All right, everybody, hello and welcome to our next topic, which is z-scores and the normal curve. So let's go ahead and take a look here at our slides. All right, so z-scores and the normal curve. This is a wonderful segue from what we have been working on. Z-scores are a direct reflection of standard deviation, and it's our first dip into inferential statistics. So insofar, we've been talking about descriptive statistics, but the concepts that we develop here, we're going to use for the remainder of the course in inferential statistics, because ultimately our goal with our statistics is to make conclusions about data. So I think you'll see why these are practical and useful and interesting to take a look at. So let's talk about what they are. What is a z-score? And let's go ahead and get me out of the way here. So what are z-scores? Z-scores are what we might call standardized scores. It takes any score from a data set and describes it in particular terms of where it fits in that data set. And it uses a couple of things to describe that fit. Those two things are some measure of central tendency, in the case of z-scores a mean, as well as variability. It actually includes standard deviation in its calculation. So specifically, a z-score will tell you how many standard deviations a particular score is away from the mean, above or below the mean. So we're going to get into some examples of why this is practical to do. But first, let's take a look at the formula. All right, got to move my big head again. Okay, here we go. Here's our z-score formula. So nothing that we haven't seen here before, right, except for z. So we're going to be solving for z here. So z is equal to x, or any given x score, minus the mean, right? So a deviation score, much like we've worked with already, divided by standard deviation. So we're actually going to start off here when we get into examples by calculating standard deviation to see how this goes, right? To see how this fits into what we're learning here. All right. So how do we calculate a z-score? All right, so we figure out the deviation score. Remember, a deviation score is how far any score deviates from the mean. So that's our x minus x bar. And then we divide that deviation score by the standard deviation, right? So let's go ahead and give that a try. All right, let's hop over to the whiteboard. All right, so we'll start out with an example. All right, let's start off with some nice and simple data here. All right, let's start off with some data. Let's say that someone took a quiz, let's call it a neuroscience quiz, okay? So let's say that these are the number of correct, true or false questions on a neuroscience quiz, all right? So we're just randomly going to grab 5 people. We're going to ask them 5 questions on neuroscience. We're going to see how many they get correct. So let me go ahead and list off a few X scores here. Let's say for our 5 people, all right, we have an N equal to 5. We get scores that look like this. Okay, N equal to 5 here. Okay, so as with any set of scores, we could begin to describe the set of scores. We could get a mean to determine the average number of questions somebody got correct. We could get the median as another measure of central tendency. So let's go ahead and just get started setting this up as we would if we wanted to find the standard deviation from the variance here. So let's get these scores in order. If we notice here, we're actually starting with a very simple data set here, but we have 1, 2, 3, 4, and 5, all right? So let's go ahead and put those down here. When we're calculating anything like this, z-scores, standard deviation, variance, we don't necessarily have to put our values in order, and when we're working with larger data sets, it's not entirely practical, but for the sake of example, I think that this might help us out here a little bit, so we'll go ahead and put them in order. So the first thing we might want to do is get a mean, okay? We remember how to calculate a mean. A mean is equal to the sum of x all over n. So we're just going to calculate the standard deviation, and then we'll go from there. I'll show you how we can easily translate this into calculating z-scores. So let's get the sum of x here. If we sum up all of these x's, we get something like sum of x equal to 15. All right, that our mean is something like 15 over 5, right, our n. So we have a mean of 3, right, a mean of 3. So if we were going to continue on calculating standard deviation and variance using the table format, remember we have two different ways we can calculate standard deviation and variance. One is using a table to find the sum of squares, and the other is the computational formula. But I'll go ahead with the table here just so you can see what we're doing here. We're getting deviation scores here, right? So x minus x bar. So let's go ahead and do that for each of these scores. Oh, not quite what we want. 3, a little ahead of myself. All right, and then 5 minus 3. Okay, so let's go ahead and get deviation scores here. All right, so what are our deviation scores? All right, we have something like -2, -1, 0, 1, and 2. All right, these in the positive direction. So we can do that trick we learned before. All right, if we sum up these deviation scores, we actually get a 0, because what we've done is we've created a center point. We've anchored all of these scores around a specific center point. So we've made equal distances on either side of the mean. And what we're doing today is actually going to help us to visualize this a little bit more. So kind of hang tight on that idea here. Let's go ahead and continue on and just calculate our variance and standard deviation. So we have our deviation scores. So now we can take our deviation scores squared. All right, deviation scores squared. All right, so -2 squared is 4, 1 is 1, 0, 0. All right, so remember when we're squaring negative values, they become positive. So we can go ahead and sum this up as well. All right, so remember that this here is, right, if we put the sum up here, this is our sum of squared deviations. Remember that nifty little SS, all right? So this is our SS. So in this case, our SS is equal to 10. All right, SS equal to 10. Let me go ahead and get a different color here. But let's remember anyway, that our variance is equal to the sum of our squared deviation scores, right, or SS all over n minus 1, or, okay, another way to think of this formula is just kind of condensed here, right, SS over degrees of freedom, which in this case is n minus 1. So we're just going to put 10 over 5 minus 1, which is 4. We get a variance of 2.5. And then moving on from here, we can take the square root of that 2.5. Let's go ahead and do so. I'm actually going to do it up here. All right, so then our standard deviation is equal to the square root of our variance, which in this case gives us something like 1.581. Okay, there's our standard deviation for this particular data set. All right, so we learned how to do standard deviation. We can get this for any given data set, but now what's something we can do with standard deviation? Well, what we can do is we can use it to convert scores to a z-score. So our z formula looks something like this. We can take any given x, subtract x bar, get a deviation score, and divide by standard deviation. Or if we think of this another way, we can just add this as a column on our table here, which is what I'll go ahead and do next. All right, I'll do a slightly different color here. So we can do x minus x bar, all right, divided by s, okay? This is the z formula. But we can go ahead and do this for each of the scores here, all right? So remember we're talking deviation scores, so we're talking these scores over here. So we can say, okay, we're going to take -2, divide by our standard deviation. We'll take -1, right? Moving down the list, 0, 1, and 2. We're going to take each of these and divide by that calculated standard deviation. Let's actually get a little more space in here, tidy this up a little bit. What we're doing here is called standardizing the scores. All right, this standard deviation is specific to this data set. All right, so we're taking each individual score and dividing by the standard deviation of this data. And what that's going to do is give us a z-score. All right, so we'll go ahead and do the math on the rest of this here. All right, so z up here is equal to negative. All right, remember we are still working with negative values here. Negative 1.265, 0.633, negative, of course, here. 0, positive 0.633, and then our 1.265 here. Okay, and these are positive. So what have we done here? We've created standardized scores, all right, that are demonstrating how far above or below any given score is. So let's take the first score here, for example, 1. All right, so now we have a z-score where if we have a mean of 3, all right, a mean of 3, we have our mean of 3 down here. If we have a mean of 3 and a standard deviation of 1.581, what we've done with this particular piece of math here is we have standardized the score of this data set to its own variability, right? Standard deviation is a measure of variability. And if we go ahead and actually sum up these z-scores, you'll see very similarly to the deviation scores, when we add them all up, it is equal to 0. We've basically anchored scores around a mean, right? Anchored scores around the mean. So we're going to go into some more examples about why this is a practical thing to do. But for now, let's consider a few other things that we can do with z-scores. So I'm going to pop us back over to those lecture slides. All right, so to calculate a z-score, we get deviation scores, and we divide by the standard deviation. In addition to getting a z-score, we can also calculate backwards. We can do what's called a z-score transformation, which is if we're given a z-score, we can do a little bit of algebra to solve for the score that z-score represents if we have some information about the data set. So we'll go ahead and do an example of this in a moment here, but I want us to take a look at these formulas so that you can see that they are just iterations of each other, right? We're just solving for a different value here. So to calculate a raw score, so if you're given a z-score and you want to move backwards to figure out what raw score that particular score is in your distribution, we can do this little bit of math here, and we'll go ahead and give that a try. So let's just take a look here. This is calculating a raw score. That's what we call them, raw scores, or the original scores, or the original metric. That's another word we're going to start using here, talking about different metrics that our data can be on. So let's go ahead and try for another example. Okay, so we started off reminding ourselves what variance is, what standard deviation is. But moving forward with these types of problems, I'll go ahead and give you things like variance and standard deviation. So let's go ahead and get a new slide here, and let's think about this a little bit differently. All right, let's say that we're looking at intelligence scores. All right, so we're looking at intelligence, right, or IQ. Okay, so let's say that we have an IQ test, that we know the average on this IQ test, so the mean will be given to you here, is 100, and it has a standard deviation of 16. All right, and this is pretty standard, right? This is pretty normal for IQ tests to have a mean of 100 and a standard deviation of about 15 or 16. So let's say that we want to learn something about our particular score. Let's say that we take an IQ test and we have an IQ of 120. All right, 120. So what can we say about that score? Out the gate, we can say that that score is higher than the mean. Right? We can say it's higher than the mean. We can even say it's an entire standard deviation above the mean. Right? An entire standard deviation above the mean. So let's go ahead and try something out. Let's calculate a z-score for these particular values. So z is equal to our score minus the mean all over the standard deviation. So let's go ahead and do the math here. If we had a score of 120, we get our deviation score, subtract the mean, and we put it all over the provided standard deviation. We end up with the difference here. And then what do we get? We get something like a positive 1.25. All right, a z-score of 1.25. So what do we make of this? Let's do some drawing. Let's get a normal curve in here. All right, let's start thinking about the normal curve and these different values that we've been calculating. So let's think about what we know about the normal curve. All right, we talked about normal curves back when we first talked about frequency distributions. In a normal curve, we expect most data to be in the center. All right, and by center, we're talking about the mean. All right, so for this particular data set, the mean is equal to 100. All right, so let's go ahead and put that here. So we have standard deviations, all right, that move out in a certain order here on our normal curve. So let's consider the following here. All right, so we have standard deviation surrounding the mean. Standard deviation represents spread or variability around the mean. So you can be one standard deviation above the mean, a standard deviation below the mean. And in this case, if you're one standard deviation above the mean, you would have a score of 116. If you're two standard deviations above, 132, and more, 148, right? Then we're getting into kind of unusual territory here, right? The further we get away from the mean, the less likely we are on a normal curve to see those types of scores. We can go the other way too, all right? Moving downward with IQ here. So now let's think about what a z-score is, all right? Let's think about a z-score. So if we think about the z-score formula, if you scored a score of 100, all right, and the mean is 100, all right, you would be looking at something like this, right, which is going to give us a difference of 0, all right? Your z-score is 0 because you're not deviating from the mean at all, all right? So a z-score of 0 means that you are at the mean for that particular distribution. But z-scores are standardized, and this is where z-scores are very nice. A z-score of 1, positive 1, means that you are one standard deviation above the mean for that particular data set. All right, likewise for a z-score of positive 2, likewise for a z-score of positive 3, and likewise in the other direction as well. Z-scores generally range from about -3 to +3. It's possible to get a z-score beyond this, but it is unlikely. And that's what we're going to move into in our next topic, which is probability. It's very unlikely that we get scores that are very different from the mean. So let's consider this score that we calculated, all right? Say you got a z-score of 1.25 on this particular test. So let's mark that here on this curve, all right? So we're in the positive 1.25, all right? So we're somewhere right about here. I'm gonna go ahead and mark it here with a line, okay? Maybe a better line than that. Let's go ahead and mark it here. This is where we're at, okay? So we can tell a few things by looking at this normal curve and by thinking about our z-score. We're above the mean, and we're above the mean by about 1.25 standard deviations. So that's pretty interesting to know, right? Especially for something like IQ, which carries a bit of weight, right? We use IQ. IQ has a bit of a rich history, but IQ was originally intended to place children in school at a level that was appropriate for them. And of course, it's taken on a new form with diagnosing different psychological disorders. But no less, it's a very useful measure. So let's say that we're interested in knowing something specific. Maybe we're interested in knowing what percentile we're in. Maybe we've heard this word, percentile. All right, so what percentile are we in? This is something that z-scores can help us to assess, all right? We're working on a normal curve here. If we want to know what percentile we're in, the percentile we're in is the percentage of people who have scored less than we have. All right, less than we have. And if we think about the curve here, we have scored better than a number of people, all right? Everybody over here, everybody below the mean, okay? And then some people above the mean to our particular point here. So this is something that we can figure out. So let me go ahead and hop back over to the lecture slides, and let's talk about a few more things conceptually before we launch into determining a percentile. Let's talk about the normal curve, all right? We're talking about a distribution that is normal, that is symmetrical, that is unimodal, that is bell-shaped. This is what we discussed previously, but we're going to continue on with a few more assumptions or considerations about the normal curve. If we have a data distribution, or we're considering scores from a set of data, all of that data exists under this hypothetical curve, all right? All of the data is underneath it. Half of it's going to be above the mean, and half of it's going to be below the mean. So moving forward, we generally assume that the information that we work with comes from a normal curve. So we can think of this in a couple of ways. We discussed this in a previous topic, but think about height, right? Most people are around a normal or average height. We have very few people on either end of the extreme spectrum, likewise for intelligence, likewise for memory, likewise for many of our psychological phenomena. So in statistics, we work on a number of assumptions, and a major assumption is that our data is normally distributed. And we're going to go ahead with that assumption here today. And we're going to use that assumption to tell us some pretty interesting information. So for something like intelligence, which we know is normally distributed, we can learn something exciting, like what percentile we're in terms of intelligence, which we'll go ahead and do here in a moment. And I am going to show the last slide in this particular set of slides, which we're going to do an example of here. So this is, of course, one of those slides I like to include steps of, say, completing a specific task, but not something I would recommend that you necessarily write down. But what we're going to do is look for area under the curve. Area under the curve is going to tell us something. If we have a great score, not many people have likely performed better than us. And if the curve is normal, we can approximate about how many people in percentage have performed better than us. So here we have a little, a few steps that might be useful to us. But let's hop back to the last slide for just but a moment here. So I want you to draw your attention to the percentages here on this image of the normal curve. So we have 50% on either side of the mean, and pay mind to the x-axis here that says z-scores. We're ranging from -3 to +3, as I drew in the last image here, and 0 is the center. So 0 represents the mean or the central tendency of the data set. So if we're at the mean, we expect that about half of people have performed better than us, and half of people have performed more poorly than us on any given task. And even more so than that, using standard deviation, a standardized score, we can determine about how many people we would expect to have performed better than us by unit of standard deviation. So notice that between 0 and +1, it says 34%. That means that we expect about 34% of all of the data to fall between one standard deviation of the mean. Between 1 and 2 standard deviations, we expect about 14%, and only 2% beyond that. So very few scores we expect to be out in the tails of the distribution. So if you add up 34, 14, and 2, we get 50, encompassing all 50% of the scores that we would expect to see in one side of the curve. If we do a little bit more math here, if we add together 34 and 14, right, we get 48% between 0 and 2 standard deviations on one side of the curve. If we add 48 by 48, we have something like 96% of all scores between -2 and +2 standard deviations. So let's go ahead and take a look back at the whiteboard here. Let's see what we're working with over here. And let's hop back to our first example here. Notice that all of these scores, all right, fall comfortably within that range. It's basically explaining that these are all within 1.2 standard deviations of the mean, which is what we would expect. Here, a score of 1.25, we can use those guidelines, all right? So let's say that we know, let's get another color here for us. So we know here, my lines have gotten a little buried, but between 0 and 1 standard deviation, we expect about 34% of people to be here, right? And we know that 50% of people are over here on the other side of the curve. All right, so we can very quickly get a general idea of how many people we've performed better than, right? If we take 50 plus 34, we can say, okay, we performed better than, say, 84% of people, and some change, right? Our change being this kind of area here. But the lucky thing for us is we have a specific tool that lets us know exactly how much data is under the curve at any given point on a normally distributed set of data. And when we do so using something called the z-table or the normal curve table. So let me go ahead and pull this up for us. This is called the z-table. You can find this in our textbook. You can also find a PDF of this on our web page. But let's take a look at this. Let's take a look at this. This is showing some normal curves. And this is showing area under the curve in percentage. All right, normal curve areas between the mean and a z-score, and from a z-score to the tail. So two different areas are being shown here. We have the percentage between the mean and a z-score, and we have percentage in the tail. Percentage meaning the amount of data we would expect to be in that given area. And if we start to scroll here, you can see that we have z-scores ranging from 0 and then down to the 100th decimal. We have these ranging all the way, all right, all the way. It keeps on going, keeps on going. Remember, most z-scores are going to be between -3 and +3. So this goes up to 3. And then if you look all the way, we're looking down at the bottom right here in the Z column. So Z heads each of these columns here. So if we scroll all the way down here, we see that it goes from 2.98 to 2.99 to 3, and then we jump to 3.5 to 4 to 4.5. Because those scores are very, very unlikely to occur, and we don't expect many scores to be beyond those scores in any given distribution. The probability gets very low, like 0.00001. All right, so we start to kind of generalize and say it's very, very unlikely that we see a score beyond this given point. And notice that there are no negative values here on the z-table, only positive values. That's because the curve is symmetrical. So the area under the curve on one side will be the same as the area under the curve on the other side. So this is a lot of information, and a lot of it is conceptual, but let's go ahead and try this out with the example that we've framed for ourselves here of an IQ score. So say we have an IQ score of 1.25, and we're interested in what percentile we are in. And what percentile means is what percentage of scores have we exceeded, right? How many people, right, if we're talking intelligence, how many other intelligence scores have I performed better than? So what do? We can take that 1.25 value and head over to the z-table. So let's go ahead and do just that. Let's hop over to the z-table here. And let's scroll down to a z-score of 1.25, and let's see what information we can get. All right, so notice our column headers here. And let's take a look back at the curve that we've created for ourselves. So if you notice here, what we've done is we've said, okay, we already know that we've performed better than 50% of people because we are above the mean. So now the area that we're interested in learning about is, let's get another color here, is the area between the mean and the z-score. All right, this area here. So not only did we do better than everybody that is beneath the mean, but we also did better than these people in here, all right? And how many people are in here? Well, if we hop over to the z-table, we can determine that between the mean and z, okay, so we're looking in the right half of this, the percentage of mean to z, and if we scroll down to 1.25, we can see that 39.44% of individuals can be found in that area under the curve, right? If this is a normally distributed set of data, which we are assuming that it is. So, hopping back over to our whiteboard here, what that's told us is that this particular area here, all right, let me go ahead and make it larger, right? This particular area is equal to what? Something like 39.44, right? 39.44. I'll hop back over to the table so you can take a look at what we're looking at. The 1.25, I need to scroll down a little bit more for us, 1.25, right, a z-score of 1.25. The percentage between the mean and z is 39.44. 39.44. Okay, so hopping back over here, let us consider this, okay? So 39.44% of people are between your score and the mean, and 50% of people are below the mean. So our percentile would be equal to that 50% plus that additional percentage that we scored higher than. All right, if we do a little bit of math, 89.44. We could say that we are in the 89.44 percentile for intelligence. And again, this is a descriptor. This is describing the data, not just describing a set of data as we've been doing so far, but describing a particular point of data. All right, any standardized test is going to do this, right? It's going to let you know what percentile you're in, because not only does it matter what score you got on that given measure, but we need to compare you to others, as bleak as it sounds, right? That's what standardized tests are for, knowing how well you did compared to, say, your peers or compared to your competitors in a given field. So let's go ahead and consider something else. Let's try out a z-transform score. So let's say that we're working with the same data here. So we're still working with intelligence. So we have an X bar of 100, and we have a standard deviation of 16. So let's say that you take a test and it's reported back to you that you got a z-score of, let's say you got a z-score equal to 2.813. Okay, z-score of 2.813. And let's say we want to work backwards and figure out what raw score or what X score this is on this particular measure. Well, we're doing a little algebra. We're kind of reworking the z-score formula. So we're going to take z times the standard deviation plus X bar. So if we go ahead and work this out, we have a z of 2.183 multiplied by our standard deviation of 16 plus 100. X is equal to, we go ahead and do this math here, and as always, I'll remind you to give it a try, even though this is a very simple calculation. At least make sure that we're kind of in agreement here, right? So go ahead and take 2.813 times 16, right? Gives us something like 45.008. All right, I'll go ahead and just call it 45. Take 45. We add the mean to it, and we get a score of 145. So this z-score, all right, raw score is 145. So we can work both ways. This is just to illustrate that the algebra or the math still works the same as we would expect it to, right? Okay. So there's our kind of foundations of z-scores. Let's go ahead and see a little bit of its more practical application. So what we're going to do now is we're going to consider two different scales. All right, this is where z-scores really come into play, is when we have what we call different metrics. Okay, so we're going to talk about forgiveness. Forgiveness, okay? An interesting variable, how forgiving is a person, right? And how do we measure forgiveness? Well, there are forgiveness scales, right? There are different scales for forgiveness. So we're going to talk about one scale for forgiveness, and we're going to talk about a second scale for forgiveness. We'll have scale 1 and scale 2. And we're going to calculate z-scores from each scale. So let's go ahead and get our z-score formula here. So let's talk about these two forgiveness scales. Let's say that you take them. You want to know how forgiving you are. So you take two different forgiveness scales. On the first one, you get a score of 25. Okay. On the second one, let's say you get a score of 60. Well, you might be thinking, what the heck, right? Those scores aren't similar at all. Well, they belong to different scales. Maybe on scale 1, the mean of all of our forgiveness scores is equal to 20, but on this scale, the mean is equal to 50. And let's even throw standard deviation in here. Right, let's say we have a standard deviation of 5 here and a standard deviation of 10 here. So we have two different scores on two different scales. All right, maybe we want to know if we perform similarly on each of these scales, right? Because our scores themselves are different, all right? These are different scores. So let's go ahead and consider this, all right? Let's calculate a z-score for scale 1. All right, I'll go ahead and just call it z1 here. So for z1, if we take our score, get its deviation score, subtract the mean, and we divide by the standard deviation, we get a difference of 5, right, over 5, gives us a z-score of positive 1. All right, z-score equal to positive 1. Let's go ahead and get a z-score for the second scale. All right, we would take our score of 60 minus the mean, that's the deviation score, put it all over the standard deviation. You get a difference of 10 up top all over the standard deviation of 10. And if you can imagine that, we get the same z-score. So even though these two scores, right, 25 is different from 60, we can say, relatively speaking, we scored the same on each of these two scales. So it helps us compare different metrics, all right, different metrics we would call them. Each of these scales on a different metric. So let's consider this, all right, let's get a normal curve going in here. All right, so we know that the center of the normal curve is our measure of central tendency, in this case, the mean. All right, so then we have z-scores. All right, z-scores are a standardized metric where a z of 0 means that you're equal to the mean. And then we'll go ahead and move out this way, all right? We got positive 1, positive 2, positive 3. And then if we go in the negative direction, negative 1, negative 2, negative 3, okay? So that's one metric, all right? We have the z metric. But let's go ahead and consider our other scales, right? Let's consider the first scale and the second scale here, all right? So for the first scale, we have a mean of 20, all right? A mean of 20 with a standard deviation of 5. So if we move up in our z-scores or up in our standard deviations, we're moving in units of 5. All right, and likewise down here, our center is 50, okay? Our mean is 50. And if we move in units of standard deviation, all right, it'll look something like this. So notice that using z-scores, when we use z-scores, we're standardizing the metric. Those scores can mean really anything within their given data set, but when we convert to z-scores, what we're saying is this represents one standard deviation from the mean. All right, so let's consider our z-score here. If we have a z-score of positive 1 on this particular measure, let me go ahead and mark that here. All right, let's say that we're interested in a couple of questions. All right, let's say we're just interested in knowing how many people are more forgiving than us. All right, then we're interested in everybody above us on this particular measure. So if we have a z-score of positive 1, let's hop over to the z-table here. All right, hop over to the z-table, and let's find 1. All right, let's find 1. We gotta go this way, going the wrong way. All right, a z-score of 1, we've found that over here. Well, not what we want. Z-score of 1 on the bottom here, and we want to know how many people scored better than us. So if we take a look at these two normal curves on the top of our columns here, we're interested in the data over in the tail. So we want the percentage in tail column to determine how many people scored better than us. So if we go ahead and scroll back down to our score of 1, our score of 1 tells us that 15.87% of scores would be expected to be above a z-score of 1. So if we hop back here, we're interested in everyone that did better than us, which is over here. This is about 15.87% of the data over here, right? So let's consider a couple more things here, all right? Let's say that you're maybe interested in how many people you are more forgiving than, all right? Well, what are some givens about this situation? We know that we're doing better than 50%, right? Because we're above the mean, more forgiving than 50% of people. But we're also more forgiving than these folk right here. All right, so how do we go about finding the area here? Well, finding the area here we can do in a number of ways, right? We can even take this as simply as saying, hey, if we have performed better than all but 15.87%, we could take 100 minus 15.87, right? And that's the remaining percentage, right? The remaining percentage on the other side of your particular score. All right, let's go ahead and get a new slide here, and let's consider a few more things. I'm going to redraw this curve here, and we're going to just keep playing with this idea of how do we find area under the curve. All right, so let me go ahead and get our some of our values back here. Oh, all right, let's get a better one. It's a little flat, but that's okay. So we have z, we have our scale 1, and we have our scale 2. Okay, so a z of 0, we got 20, we got 50, so we got 1, 2, 3. Remember, we're just moving in standard deviation units, so the standard deviation for scale 1 is 5. So we'll go ahead and move in units of 5, and then likewise down here, but for 10, okay? So let's get these values in here as well. Okay, then we have 15, 10, 5. All right, we'll move backwards in this way as well. Okay, so remember the center is representing the mean here. So let's consider a few more things. Let's say that your friend takes scale 2, okay? They take scale 2. All right, so we had a score, right? Our z-score was equal to 1. So I'll go ahead and put us, we'll be this bright green, okay? That's us here. So our friend takes scale 2, and let's say they score as follows. So remember, scale 2 is this one here, right, with the mean of 50. So they take scale 2, and they get a score. We'll go ahead and call it x3 here, because we had x1 and x2. Let's say they get a score of 65. We're going to score 65. So if we do our z-score formula, all right, we're going to take that score minus the mean, get a deviation score, and put it over the standard deviation. All right, so 15 over 10 gives us 1.5, the z-score equal to 1.5. So let's go ahead and put them here. All right, they're here at 1.5. So let's say, all right, we already know how many people scored better than us, right? That was the 15.87, okay, that we found over here, right? That's who did better than us. But if we hop back over here, let's say we want to know how many people did better than this friend of ours, right? Let's hop back over to the z table. All right, so now with the z table, we're interested in finding a z-score of 1.5. Let's go ahead and move over here. So if we want to know how many people scored better than a z-score of positive 1.5, we want to know how many scores are into the tail beyond a z-score of 1.5. So if we take a look at the percentage and tail column and the row that 1.5 belongs to, you'll see the value 6.68. 6.68. So let's hop back over here. All right, so 6.68% of people scored better on this forgiveness scale than your friend here. But let's go ahead and consider one more thing, all right? Let's say that we specifically want to know the difference in percentage, right, of how much better your friend scored than you. Well, if we know that the distance from their score to the tail is 6.68%, and we know that the distance of our score is 15.87%, we can simply get a difference of our scores, right? Then that would tell us the area that is between us, right? Or the percentage of people that scored in here. So if we get the difference between 15.87 and 6.68, we get something like 9.19, right? That's the area between these two scores. So hopefully you can start to see how really creative we can get when it comes to addressing area under the curve between scores, right? Remember, this is about half a standard deviation of difference. But remembering those rules, okay, that there's about 34% of data between one standard deviation and the mean, 14% beyond that, and 2% even beyond that, we can start to get a general idea here of how we can interpret this, right? Or how we can get, say, percentiles. So let's go ahead and try getting percentiles for these particular scores. All right, so percentiles are the percentage of people that we scored better than, right? So let's freshen this up again. All right, we're getting a little bit of chaos going here. All right, so 1, 2, 3 standard deviations away. Okay, so we're at 1. Our friend is here at 1.5. So again, we know that 50% of people are over here, right, beneath the mean. And we can even say for ourselves, right, because we remembered those figures, there's about 34% of all of the data right here. So we can go ahead and say, right, that our percentile for person 1 here, right, our percentile is going to be something like 34 plus 50. That's just eyeballing it, right, about 84%. Let's go ahead and see how we would figure that out in the table. So if we head over to the table, so we know that beneath the mean there are 50% of the scores, but we're interested in the percentage between the mean and z for a z-score of positive 1. So we're over here in the percentage of mean to z, and we're moving down to a z-score of 1, and we see 34.13. That's fairly close, right, to what we said before, right, that we expect 34% of data to be here. So if we're going exactly from the table, this would be something like 84.13, right? We can do the same for our other friend here, right, for this person, or if we know that they scored better than 6.68% of people, we can simply take 100 minus 6.68, get something like 93.32%. All right, and that would be their percentile. Okay, wow, we've covered a lot, haven't we? But let's just do one more little set of practice with raw score conversions, all right? So this is what we call raw score conversions. All right, let's do some raw score conversions here. So let's do it for scale 1. All right, and let's also do it for scale 2 here. Okay, so let's say for scale 1, we have somebody who has a z-score equal to -2. And over here for scale 2, we have someone with a z-score equal to positive 1.75. All right, so to convert this score to a raw score, we'll need to take that z-score times the standard deviation of that data set plus the mean. All right, and likewise here, x equal to z times s plus x bar. All right, so let's go ahead and do this. We have a z-score of -2, and on our first scale, we had a standard deviation of 5. All right, and then we had a mean of 20. All right, so if somebody has a z-score of -2, we would say, okay, we have -10 here plus the mean of 20 means that they have a forgiveness score of 10. All right, let's go ahead and do the same over here. X is equal to our z, 1.75, times s, in this case is 10, plus our mean of 50. So x is equal to 17.5 times 10 plus 50 gives us something like 17.5 plus 50 equal to 67.5. All right, and these should make some sense, right? 10 is below the mean, all right, which we would expect from a negative z-score. 67.5 is above the mean, which we would expect from a positive z-score. So this has been the basic mechanics of z-scores. We will be practicing z-scores more and comparing across metrics. And we move into probability, which uses these ideas as well. So I'll go ahead and see you over in the homework review where we talk about these topics more.